In previous lectures, we learned about the important distinctions between the behaviors of linear and nonlinear systems. But we haven't talked about how to distinguish a linear from a nonlinear system given the equations of motion. Sometimes we can do this simply by testing for superposition to see if it holds, but we'd like to find a way to do it by inspection so that we don't actually have to go through the mechanics of a full superposition test. Toward that end, in this lecture, we'll look at a method to distinguish linear from nonlinear systems. This won't work on just any linear or nonlinear system, but it will simplify the task for many systems. In this lecture, I'll present a technique for distinguishing between linear and nonlinear systems, and this will work on a subset of all possible systems that we might consider. The only test that can distinguish between all linear and nonlinear systems is a superposition test. The test consists of 4 steps, and I'll go through these first, and then we'll do some examples. So the first step is to identify signals and parameters. Whenever we're given an equation of motion, the input and output signals will be identified. There will also be internal signals, and internal signals are any time-varying quantity that is affected directly or indirectly by the input. All other time-varying or constant quantities in the equations I'll refer to as parameters. So for example, if we're given the differential equation at the top of the page and told that this is our system with input signal x of t and output signal y of t, then we can come to the following conclusions. Signal x of t clearly changes y of t, and if it changes y of t, it must change y dot and y double dot. So y dot and y double dot are internal signals. X of t won't change cosine of t or the function f of t. Both of these are explicit functions of time. So those are parameters. The second step in our procedure is to clear denominators, expand all products, and cancel all like terms. So for example, if we're given the differential equation shown at the top, we would get rid of the denominator by multiplying both sides by y. We would take y minus 1 squared and we would expand that term out, and then we'd drop the like terms, in this case y squared. Our third step in the procedure is to separate the expressions into terms, and this separation occurs at the following symbols: plus, minus, equals, and integral. So for example, if we were given the differential equation y dot plus cosine ty equals x minus x squared plus integral from 0 to t x of tau d tau, we would have the terms y dot cosine ty x squared and x of tau. Note that time integral symbols are dropped when we're finding the terms. In step 4, we are to write each term, if possible, as p times s, where p is a function only of parameters, constants, and time variables, and s is one of the system signals. If every term can be written in this way, as p times s, the system is linear. If not, the system is almost certainly nonlinear. We can't be absolutely positive. It requires a little bit of thinking to see if there's any way that it could be transformed in such a fashion to make it into p times s. But if you're certain it cannot be transformed, then it is nonlinear. So here's the example that we considered in step 3. We identified the terms of this differential equation as y dot cosine ty, x, x squared, and x of tau. Let's look at each one of these terms and see if we can write it as p times s. Y dot certainly can be written as p times s, where p is equal to 1 and s is y dot. Cosine t times y can be written as p times s, with p being cosine t and s being y. X, of course, can be written as p times s, but x squared, that cannot. We can't write that as p times s. We'd have to choose p to be x and s to be x. But p cannot be dependent upon a signal, and x is a signal. So that one looks like it's impossible. The last one, x of tau, that can be written as p times s with p equal to 1 and s equal to x of tau. So every term here, except for the x squared, can be written as p times s, but the x squared can't, and it doesn't seem possible that we could multiply or divide the whole equation by some term so as to make the x squared nice and keep all the other terms being p times s. So we conclude the system is nonlinear. Let's now do another example. So our equation is y dot plus h of t times y equals integral from 0 to infinity m of tau x of t minus tau d tau. And we're told that the input signal is x and the output signal is y. So y is clearly changed by x, so we know that y double dot is an internal signal. Our parameters will be h of t and m of tau. So now we separate out the equation into the terms. We have y double dot, h of t, y of t, and m of tau, x of t minus tau. Let's now check each of our terms to see if they can be written as p times s. Y double dot certainly can, p equal to 1 and s equal to y double dot. The second term, h of t, y of t, we can write as h of t as p and s is y of t. And our last term, m of tau times x of t minus tau, well, p can equal m of tau and s can equal x of t minus tau. So we're good on all three terms, and so this system is linear. Here's a third example, and in this example we actually have two equations of motion. The first one, y double dot plus 3y dot equals z, and the second one, z dot equals t times x. Our input signal is again x of t and the output signal is y of t. Our internal signals will be y double dot, y dot, and z dot. All of these are changed by the signal x. The parameters are 3 and t. These are certainly not changed by the input signal. So now we'll find our terms. In the first equation we have y double dot, 3y dot, and z. And in the second equation we have z dot and t times x. So now we'll check each of our terms to see if they can be written as p times s. And in fact, every one of these terms can be written as p times s, as shown below. Therefore we know that this set of equations is linear. Let me now show you a tricky problem. And this is the reason why distinguishing linear from nonlinear systems can sometimes be difficult. So we're given two equations of motion here. Y dot plus y equals 1/2 z squared, and z dot equals x over z. The input signal you're told is x, and the output signal is y. The internal signals will be y dot, z dot, and z. And the only parameter is 1/2. If we carry out the steps, the z squared term will indicate that this system is nonlinear. But let's suppose we try to eliminate the internal signal z. We'll take the equations of motion. and we'll write them as in the right-hand corner. Y dot plus y equals 1/2 z squared, and z dot equals x. We'll take the time derivative of the first equation, and that will give us y double dot plus y dot equals z times z dot. And since z times z dot is equal to x, we can substitute that in and remove the z from the equation. That gives us the equation y double dot plus y dot equals x, and this is a linear system. Let me be clear. The input-output relationship between x and y is linear. It obeys superposition. The reason why it appeared nonlinear was because the way it was written in terms of its internal variable, z. Nonlinearities that occur between the internal signals and the input and output may disappear when the internal signal is eliminated from the equations. This is not something to be terribly worried about. This won't usually happen in most systems. It's a rather atypical case. You can be certain that this will not happen if all the internal signals are time derivatives of the input or the output signal. In spite of the trickiness of this last problem, I think you'll find this method works on most problems, and hopefully it'll be beneficial to you in solving homework problems. These methods of classification are very important because they can help us understand what kind of behaviors a system can or cannot display.
How do you solve this? I don't even know if this is linear or non-linear. Alright, boy, I'm gonna tell you how to see through these blurred linearities. Variable plus.
I didn't know math could work that way. Your inputs and outputs, relations too hard to gauge.
Maybe I'm going dumb, maybe I'm going deaf, maybe I'm mathing out of my depth.
Variable plus.
Okay, now I was told, try to determine nature, but you're highly perturbable. Baby, it's in your nature. Canospi is the maker. Should I approximate her to fix her bad behavior?
Variable plus.
Good function, additivity, I want it. Homogeneity, I want it. Superposition, I want it. Draw a bad function. Fella's getting past me. This math getting nasty. Got a test next week. Need a drop med key. Need these blurred linearities. Additivity, I want it. Homogeneity, I want it. Superposition, I want it. A bad function. Your isolated equilibrias, giving me ventricular arrhythmias, turning my mind to vestigious.
Variable plus.
I'm gonna make a good function. Additivity, I want it. Homogeneity, I want it. Superposition, I want it. Draw a bad function. Your output's highly conditional. Chaos based on conditions original. Making my test score abysmal.
Variable plus.
Hate these blurred linearities. Additivity, I want it. Homogeneity, I want it. Superposition, I want it. Or a bad function. Subharmonic oscillation conditional. Based on your conditions original. You the most chaotic function in this test. A bad function. Your limit cycles just ain't rightful. Cause my grades they stifle. Ain't no trifle.
Yo, I'm gonna tell you how to figure out these blurred linearities.
My engineering damsels. Step 1, identify parameter and signal. Now it's time to make your equations lean. Step 2, expand products, cancel terms, so your denominators is clean. Now separate the wheat from the chaff. Step 3, separate expressions in parameters, minus, plus, give time integration the shaft. Now take all these terms and it's time to distill, because write each term as parameter times signal. And if you can do step 4 for each term, then you've no need to stir. Your equations is linear. But if you can't, man, you in danger. Non-linear, baby. Switch to an art major. Function, additivity, I want it. Homogeneity, I want it. Superposition, I want it. Draw a bad function. Fella's getting past me. This math getting nasty. Got a test next week. Need a
drop my key.
Now I got this. We're gonna take it to the frequency domain. Let's get frequency with it. Hey students, one thing I ask of you, let me be the one you back that math to. From Paris all the way to Malibu, dealt with equations twice as bad as you. So students, just hit me up when your patience is through. Give y'all something to tear that test into. Laplace transform and your troubles is through. Swagging the frequency domain. I mean, it's almost unbearable. In 228 years not there would I hang in the time domain and let you pass me by. Nothing like your last transform, it couldn't handle you. It don't take that math and simplify like that. Differentiation to addition, engineers salute. Laplace transform this mathematical brute. I know I'm good, other transforms just can't help hating, cause no linear function can refuse my integrating. When you take it to the frequency domain, you get the mathematical cavalry. Laplace transform, you done in two, time to begin the ravelry. That's right, man, test is over, regain your composure, cause after you learned Laplace, Mech Systems was over.
Variable Laplace.
Get me.